Okay, ready, Boris? Okay, so it's our pleasure to have Boris Nectoux. Boris is an assistant professor at the University of Clermont, which is in the center of France. He's working mainly on metastability phenomenon in statistical physics, quasi-stationary distributions, and Eyring-Kramers formulas. He's part of the probability and statistical team. His PhD advisors are Eric Cancès, Tony Delivier, and Dorian Leclerc.
Both in the room.
Thank you both for trying to talk in my French, and I apologize.
No, it's fine. I mean,
Was this right here?
thank you very much for the introduction. So let's get started. Before I start, I would like to thank the organizers for the invitation. So I'm going to speak about the derivation of the law of large numbers and the centrality theorem for two lower neural networks. So in the case where there is a mismatch and some noise. Okay, so the joint work is Arnaud Descoux, who is finishing his PhD at the back of the room, and Arnaud Pia and Manon Michel, three at the LMVP, so Clermont. Let's start. So there will be mainly 4 parts, I would say, but we will probably have time to deal with the 2 first parts. In the first part, I will introduce the model and the 2 main results. So law of large numbers and the centrality theorem. After, we'll see how the proof of the law of large numbers works. I will sketch the proof of the centrality theorem, and then we'll see some extensions to Bayesian neural network at the end. So the model and the 2 main results. So the model we will consider is the following 2 lower neural network. So I wrote it here. I don't know if you can see it well at the room, but it's written here. So N is the number of neurons. Okay, it's the number of either lower. X not the input data, it's in Rn. Sigma star is the activation function, nonlinear, priori. And W are the vector field recording all the weights. So you have n weights, which all belong, each of them belonging to R to the power d. So this is the dimension of each weight. Y is not random. And as you probably all know in the room, so there is nothing new, you want to find W so that your neural network G is close to 1. Okay. So for that, what we consider is the standard average square distance. So this is this expectation between G and Y when X and Y are distributing according to a probability distribution on X times Y, which are the probability in the space for X and the space for Y. Okay. And because, as we said this morning, we don't know pi, we approximate it over a random batch. So B is a batch. This is the cardinality of the batch B, so the size of B. So this is approximated with this quantity, where B is the random set of identically distributed variables according to that. Okay. So to train the neural network, as we saw many times in this conference, so nothing really new in this, we use the stochastic gradient descent, so SGD. So with noise, so we'll cover this term in a few seconds. So WK plus 1, Y. So K will be the step of the gradient descent, and Y, the level of the neuron. Okay. Y is in between 1 and n. You have n neurons, and K is a non-negative integer. So WK plus 1 is WK minus alpha, the gradient of this functional with respect to W, evaluated at WK. Okay. And all the initial weights are distributed independently according to a fixed probability measure on RT. Okay. So let me now come to this additional term. So this term is a negative noise term. Is added to help exploring the energy landscape. Okay. So what are epsilon ak and beta in this expression? Epsilon ik is a sequence of normally distributed, centered normally distributed variables which are independent from each other and dependent of all the other variables. The noise here scaled with respect to n to the power beta. So beta is nothing more than the intensity of the noise. It's a non-negative real number. Okay. So we introduce the empirical distribution of the weights of the neural network. So this is this quantity, and actually we could study its scale version. Okay, so for time t, Okay, mu t is nu, so the empirical distribution taken evaluated at time integer of nt. Okay, so I wrote it here. Okay, so you keep this in mind in order not to be lost. So mu t has the following expression. Okay, and when n goes to infinity, so when the number of neighborhoods goes to infinity, also the depth of the gradient descent goes to infinity linearly with respect to n. Okay, and so because we are using the integer function, okay, here we see that mu n is a random element of this space. Okay, this space is nothing more than the space of Cadillac function from R plus to the space of probability measure. Cadillac function continuous from the right, limit when coming from the left. Okay, so G will always refer to Cadillac function. Okay, so there are two goals. We need two goals in this talks. The first one is, can we prove that mu n satisfies the trajectorial law of large numbers? So is there a limiting process in trajectory for the scale empirical distribution of the weights? And if the first point is satisfied, can we, when we consider mu n minus bar mu, the limit of mu n times square root of n, can we prove that this process, the fluctuation process, has a limit when n goes to infinity? Okay. So these are the two goals we will focus on, and there are of course related results in the literature. So the first one is that the law of large number at fixed time t has already been derived by May and Montanari and Guyenne 5 years ago. And with formal computation, a law of large number and the central limit theorem were derived in the work with by Rotzkopf and Van den Eyden. Our work is, I would say, very close to the work of Sirignano and Spiliopoulos. So there are two works, actually, a low large number and a central limit theorem, probably at the same time. Okay, so except that here we consider the batch and the case. There are also other differences that I can explain at the end of the talk if you want to how we work in this work. So we will work with a set of assumptions. So the first, we introduce integer gamma. Okay, so gamma is I'm not saying that gamma will be optimal in the following, but gamma is the dimension of the weight of a weight divided by 2 plus 1. Okay, and we assume that pi and mu naught has a moment of order gamma. Okay. We also assume that the activation function sigma star is smooth, but doing more computations, it's, I would say, you have great chances to get the same result if you consider, for instance, the Relu function, which has only one singularity, and it's not that bad singularity.
We can ask the question. I think D was N in the beginning. What's the difference between small n and D?
Sorry, I don't understand the question.
There was a small n at some point. No, I think n is the number of neurons. Big set.
Which one? This one?
Small and then.
What is the difference between small and Z?
So with this n and D, so D is a dimension, as you can see, D is the dimension of the node. Okay, and n dimension of the node. Okay, so I'm not considering. No, not like we saw yesterday. I'm not considering the limit n. So it's too many. Yeah, I didn't really comment on Rn because we are not interested here in the limit n goes to infinity as yesterday. Yes, I'm answering the question now. Okay, so we introduce the Wasserstern space, which is the space of probability measure admitting moments of order gamma. Okay, and it's endowed with its standard Wasserstein distance. So we won't really use expressions, or just wrote it like this, but we can skip it for a moment. And the first result is a trajectorial law of large number for the scale empirical distribution of the weights. So this is the following theorem. So let us assume that beta is strictly larger than one half. Okay, so we will see the case when beta is equal to 1/2 in the next slide. Okay, then we prove that mu n, so the sequence of scale empirical distribution of the weight converges in probability in the space of Cadillac function with values in p gamma, okay, towards, so it's converging in probability towards the deterministic element, okay, which is the unique solution of the evolution nonlinear measure value equation, which is the following equation. So mu bar is a unique solution of this equation. This equation is non-linear, mostly I would say quadratic, because you have mu bar here, okay, and you also have mu bar here. Again, it's an evolution equation. Okay,
So what do you mean by deterministic element here?
mu bar is a function independent of any event. So it's a fixed one. So yes, it's there is no randomness in the.
So it's like a Dirac measure.
Exactly. If you prefer, the law of mu n converges
Okay.
towards Dirac evaluated at value. Okay, but it's in terms of a random variable. If you prefer with the measure, it's a Dirac. You completely right.
What's the topology of D?
Indeed. Well, there are many topologies for the square record space. We use the standard one you can find in the book of Billingsley, for instance. Okay. You have G1, G2, G3.
The convergence of all topology.
No, the topology it really depends. It's a bit different. I mean, it's not like for continuous function, you have to be a bit careful with the topology you consider on the square record space. Okay. Okay. So now I turn to the case when beta is equal to 1/2. Okay, and so when beta is equal to 1/2, actually you can prove that the same result holds, except that you have an additional Laplacian term in the limit equation. Okay, and this should not be really new. I mean, for those of you who know the paper of May and Montari in India, okay, who derived the law of large number at fixed time. Okay, so now we turn to the second result. The second result is a central limit theorem for the fluctuation process. So we have answered the first question. Okay, so we have the law of large number. So now we take mu n, the scale of the numerical distribution of the weight, okay, minus the limit of mu n and multiplied by square root of n. And the question is, how does it behave when n goes to infinity? Okay. So let me just tell you that actually this process is not a probability measure anymore. Okay, it's not necessarily non-negative. Okay, so the sign measure and the dual space of sign measure is very ugly. So for this reason, actually, we work in the dual space of some Sobolev spaces. Okay, but I just want to make a remark. Is that actually there is an alternative possibility, and I discovered this 2 weeks ago, discussing with Benjamin in Nancy, that you can also derive this result using a so-called Lyon's derivative. Okay, so just in the future, I was really interested in this kind of thing, but we won't consider Lyon's derivative. So let me introduce the Sobolev spaces we consider. So there is only one, so the norm we consider here is to take a smooth compactive supported function in RD. Okay, we consider this norm based on our norm of all the derivatives up to order L. Okay, and you take the completion of this space with respect to this norm, and you're left with the space HL. This is the Sobolev space we consider. It's a Hilbert space. You can consider it with dual space that we write that we denote by h to the power minus L. Okay, and the bracket pairing a function in HL and an element in the dual, just simply written like this. Okay, say standard Hilbert spaces, and with these spaces, you can prove actually with Sobolev spaces, you can prove it's not that difficult that actually the fluctuation process is an element of the Cadillac space of function with values in the dual space of h to the power minus L. So for some L sufficiently large depending on the dimension, unique sum injection. So we will see what is L in the coming slide. So and the goal is to derive the central limit theorem. So what happens when n goes to infinity? So there are two technical assumptions. The first one is we assume that mu naught is compactly supported. Okay. That's not a big deal, I would say, and we'll assume that the batch. So if you remember, at each step of the stochastic gradient descent, we consider a batch, pk, and we assume that the size of the batches when k goes to infinity converges almost surely to right to infinity. Okay. So there is this. So because the limit equation for the fluctuation process involves a process that we have to define. So the G process, I have to define it now. I mean, it's a big. I would say there are a lot of formulas that we will not really look at it precisely. I just define a G process as a process. It's an infinite dimensional process which is continuous with values h minus L. Okay, so this is the G process we define, and well, it is defined as the following processes. So if you take any, for instance, basis of HL, orthonormal basis, okay, of HL, and you project it, so you are left with a vector of size k. Okay, you want it to be continuous, to have zero mean, independent Gaussian increments, and with the following covariance structure. So don't really look at it, just that this covariance structure involves the limit of mu n. So what happened was the deterministic element appearing in the low of large numbers. So don't really look at it, it's pretty ugly. I would say just remember that the G process is zero mean independent Gaussian increments with a given covariance structure. Okay, that's okay. And the central limit theorem is the following. Okay. So let's assume that beta is, so the intensity in the noise, if you remember, the intensity of the noise in the stochastic gradient descent is strictly larger than 3/4. And because now you know me, you know that in the next slide, I will discuss the case when beta is equal to 3/4. Okay, so let's first focus on this case. Okay, and assume that L is larger than 2D plus 8. And I can directly show you that it is absolutely not optimal. Okay, this is just something okay, for in Sobolev injection, probably you can have a better bound. Okay, so L is the exponent of your Sobolev space, okay, in which we work. Okay, so the fluctuation process converges in distribution in the space of Cadillac function with value in h to the power minus L. So now we are not in the space of probability function as before, okay, but we are in h to the power minus L, okay. And it converges now to a random process, so it's not deterministic anymore. And this random process is continuous. It's not Cadillac anymore, it's continuous, value in h to the power minus L. Okay. And it's the unique solution of this, actually the quick unique solution of this stochastic linear equation. Okay. It's linear because US appears here and here, but if you do a lambda US, you're left with something to tell you that you have a linear equation. So it's not linear as it was in the law of large numbers. Okay, and at the end you have a G process. Okay, so there exists a G process that it's a weak solution. So you have the unit of the weak solution. So only the law of mu that really matters. Okay, so it's very similar to the previous result, except that delta is now not the process. Just a quick remark is also that we have, because we have considered the case, the batch case, I would say, we have so run some numerical simulation to observe the variance reduction of the fluctuation process when the size of the batch increases. Okay. So now the case when beta is equal to 3/4, then you can observe that things are actually, in a mathematical point of view, things are much more complicated. But you can derive, you can prove that actually it should work the same, okay, but with an additional linear term in T in the linear stochastic equation. So for instance, if you take D is equal to 1, I know it's absolutely not yes.
So you have uniqueness
Of the weak. Yeah, because we're only interested in the law. So actually you need weak uniqueness.
Yeah, so do you have a unique weak solution?
Yes, yes. So we are, yes. So, exactly like for stochastic differential equations, but you replace Brownian motion by G process. Okay. Let us assume that this is equal to 1, so it's absolutely not relevant for applications in machine learning, but just mathematically to see what we can have. Okay, so we are far from D goes to infinity. F2 is equal to x to the power x to the power 2. And if you can show that eta n has limit points, weak limit points in the back topology, okay, and its solution of the weak solution of this equation, and you have an additional term, okay, mostly coming from a low number from the epsilon, okay, which are independent. Okay, and so you can observe numerically this linear dependence in T with a numerical simulation. Well. So that's all for the main results. So now we go to the proof of the law of large numbers. So when things are starting a little bit more mathematical, I would say, so I'm sorry, it's the end of the day. So we try to be short. I will call you what we want to prove. We want to prove the law of large number. Okay, we want to prove that the scale of empirical distribution converges in distribution and its whole trajectory towards a deterministic element, which is the unique equation of this nonlinear measured value equation. Okay, so the proof scheme is divided into 4 steps. Okay, the first step, so I should probably start with actually the slide just after. just to tell you that the proof scheme we use actually is mostly inspired by, works on interacting particle systems, okay, mainly from the studio of infill interacting particle system, and it goes, I would say, I'm not exhaustive here, but I would say it comes back probably to Schnitzman, and after you have work by Roger and Méléard, also at the end of the 1997, 1998, so these are four works, but actually absolutely not, I'm not absolutely not exhaustive. Okay, so I'm sorry if I missed something. And the proof scheme is the following. Okay, so inspired by these works. The first step is you want to identify the limit equation. You want to reveal the limit equation. Okay, once you have revealed the limit equation, you want to pass to the limit in this equation. Okay, but to pass to the limit, okay, you need to have limit points. So you need to be relatively compact. Okay, so you have to prove that for the right topology, UN is relatively compact. Okay, once it is relatively compact, if you want to pass to the limit, you have to prove that you have error terms in your pre-limit equation and continuity in the right topology, so you can pass to the limit. Okay, so very standard proof. It's also the same for construction of solution of in partial differential equations. The same compactness argument. Okay, and because you want the whole sequence to converge, you would like to prove at the end that there is uniqueness of the limit equation. Once you have a limit, once you pass to the limit, you prove that every limit point is solution of this equation. This equation is a unique solution. So you have only one limit point. You are relatively compact. So the whole sequence converges to the solution of the limit equation. Okay. So it's a proof by compactness. So I can anticipate directly a question is because we use compact argument. We don't have bounds in the convergence. Okay, we don't have bounds with respect to n. Okay, we don't know how fast mu n converges to bar m. Okay. Well, let us derive the pre-limit equation. So we'll do very simple computations. Okay, recall that the scale empirical distribution is by definition the empirical distribution taken evaluated at integral of NT. Okay, and so just do a telescopic sum. Okay, so nothing really difficult in this. I add, I remove, I add, I remove, I remove many times. And so I'm left with this equality. Okay, I recall that by definition. So f is a smooth function. Okay, compactly supported. No problem for this. It's closure. It's closure is the subpolar space I consider. So I would say the right test function. Okay, so f mu k evaluated at f as this expression. Okay, and so I do the difference between, because here now you want to know what is inside. Okay, so it's different between uk plus 1 minus uk, and so this is what I do. Uk plus 1 minus uk. So this first line is just by definition. Okay, wk plus 1 minus wk. And now I do a simple Taylor-Lagrange formula up to order 2. Okay, for wk plus 1, and so I'm left with the dividend of f and the difference between wk plus 1 minus wk. And a term involving the Hessian matrix, the second derivative of f, evaluated at a point in between wk and wk plus 1. Okay? Okay, so that's standard computation. And if you see here, okay, I have wk plus 1 minus wk and wk plus 1 minus wk. I use the stochastic gradient descent algorithm. Okay, and so they are linked with the following, okay, expression. Okay, this following formula. So I take it, I plug it, okay, and I'm left with this quantity. Okay, so just rearrange some terms, but nothing really complicated. Okay, and I inject this difference now, okay, inside the first difference between ut and mu naught. Okay, so this is equal to this. I plug it again, and I'm left with this formula. Okay, so I just forgot to tell you that this term actually will always be an error term. I call it R. Okay, so the name for R. Okay, and I'm left with this quite ugly formula, and with this ugly formula, you don't see the limit equation. For me, I don't see. Okay, but we will just rearrange some terms in order to reveal the limit equation. Okay, so for that we will use two processes. Okay, the first one is M. Okay, M for martingale. Okay, and this is this process. So, okay, don't look at it; it's quite ugly. Okay, and VT is an error term. Okay, you can see it's an error term because in the integral you go from integral of NT divided by N to T, so it's of order 1/n. Okay, so this will always disappear. Okay, but M is a martingale. You can check it. I mean, but the formula is very easy. So you use these two processes in this formula. Okay, and you're left with this pre-limit equation. Okay, and in this pre-limit equation, you have the limit equation here. Okay. Once you have the limit equation, okay, what you want to do with the pre-limit equation, because you have revealed the limit equation, you want to pass the limit n goes to infinity. And as I said, for that you have to prove that the process has the un as limit point. Okay, so let us turn now to the second step. The second step now consists in proving that un as limit point, it is relatively compact in the root topology. And that function, so these values p gamma. So for that, we use a criterion. Actually, it's a Jakubowski criterion, so 30 years ago, which is this criterion, okay, because mu(n) is in value with p gamma. We will try actually to simplify a little bit the criterion by considering real value the sequences. So mu(n) is, which is in this space, okay, is relatively compact in this space, okay, if the following two conditions hold. The first condition just tells you that the process lies with high probability in the compact of p gamma. Okay. The second one tells you that when projected, when evaluated as smooth compactly separated function, okay, the sequence is relatively compact in this space. Okay. And so you may wonder, okay, and it is normal, I would say, that this is a bit weird because I replaced relatively compact by relatively compact in the second item. Okay, so I mean, yes.
And why is it intuitive to introduce the process?
Oh, actually, just let's working with the martingale, I would say it's quite natural. Okay, so you just center it. Okay, and actually, this is something which is quite standard, I would say, when studying interacting particle systems. So you try to find the martingale process, and also you approximate all your sum here. Locally, which are locally constant. You see, it's locally constant here because you have integral of NT, and so this you can, I mean, just write that it is the integral over NT of a locally constant function plus one, and this is what is missing is the sum until NT integral of NT minus 1. Okay, so this is missing in the integral. Okay, and so you have the integral minus the integral, and you have NT. Okay, coming from the file. Okay, so actually the second item, so let us come back to this criterion. Actually, the second item is easier to characterize, to prove, actually, because you can use very standard criterion like the one given in the Phoenix layer with Ecur's books, so standard textbooks. Okay, so use the favorite relative compactness criterion. There are many of them in the textbook. Okay, so how we derive item 1 and item 2? Okay, so to derive item 1, you have to know what is the compact of p gamma. If you don't know what is the compact of p gamma, you study. So you need a characterization of some compact of p gamma. It's an equivalent, but all the probability measures which have moment of order strictly larger than gamma, okay, uniformly bounded, this is the compact set of p gamma. Okay, so this is the standard result, and we can find it in the book of Villanis book, for instance, but there are many other books. Okay, and the book is straightforward, I would say. Oh, on p gamma? On p gamma, consider the Weierstein topology I introduced at the beginning. Okay, but I don't want to work to say more on this. Okay, and if you want, but now you know what is a compact set, and so we can prove actually using moment estimates, okay, the pre-limit equation, that the scale empirical distribution has bounded moment uniformly in N and in T of order gamma plus epsilon. Okay, so with combining this result with this one, you get condition 1. Okay, so it lies in the compact of P gamma. Okay, with high probability. Once you have the expectation, it's a Markov equality to prove that with high probability you are in such a compact. Okay, so now for the condition, second condition is I would say a little bit blurry if I write it like this. So we can actually prove that you need a regularity condition. Okay, you need to control mu t minus mu r uniformly in the differences between t and r with the function f and delta, which satisfies this asymptotic condition. Okay, so it's a little bit too much information, but with this criteria, which I would say really looks like, if you know Ascoli theorem, okay, it really looks like Ascoli theorem, but you have to be a bit careful because you work in the Cadillac space. Okay, so we are not continuous anymore. Okay, and combining this result with the proposition, you derive condition 2. Okay, so in the conclusion, you prove that UM has limit point in distribution for the right topology. Okay, so you need to believe me a little bit for this because I understand that it's probably too much information. Okay. So now you have limit points and you want to prove that this limit point satisfies the limit equation. So you want to pass to the limit in the limit equation. Okay. So you want to prove that this will behave nicely. Okay, so you can pass to the limit and you remove the n. Everything is fine. You're left with the limit point here, the limit point here also, and all this will actually vanishes in the limit n goes to infinity. Okay. So this is the purpose of the next slide. You have to study the continuity property of this functional. So this functional is this functional minus the first one. Okay, with respect to the involved topology. Okay, unfortunately, this functional is not really continuous. Okay, you can prove that actually it's only continuous. So when Mn converges to M in the right topology, you can prove that f of Mn will converge to f of M only if M is continuous at T. Okay, but you work a little bit more, and once you work, you can pass to the limit in the equation. Okay, so with more works, I would say you can do it. And then you prove that this goes to 0, so the remainder term goes to 0, and actually this is true in L1. Okay, you use the standard continuous mapping theorem, and you can pass to the limit. Okay, so we now go to the last step. Okay, and you have to prove that you know that any limit point of mu n satisfies this equation. You want to have only one limit point, so you need to prove that this equation has a unique solution. Okay, so to prove that it has a unique solution, we can prove it that it's a space of continuous function with values in P1, so with moment of order 1. Okay, and so we have to prove that, work a little bit more to prove that any limit point in the space of Cadillac, the topology of Cadillac function actually is continuous. So you have to control uniformly the jump of mu n with respect to n. Okay. So the standard criteria, for instance, in the book of Jacob Chirayev, for instance, to do this. And to show them that it admits a unique solution, we use PDE techniques which have been developed by Piccoli, Rossi, and Trella, and Piccoli and Rossi, I would say 10 years ago. Okay, and once you have you use this result, you adapt it and you adapt it to your setting, and once you do it, actually you are done because you have proved step 1, step 2, step 3, step 4. So you're done, and so you have the low Flash number. Okay. Just to say a word, I have introduced a martingale term. Why did he introduce a martingale term? You don't use it. Actually, for the low Flash number, you don't see it. Okay, the martingale term does not produce anything for the low Flash number. But when you multiply by square root of n, it converges towards the G process. So this is why we see the G process in the central limit theorem. Okay. Well, just a word to tell you that actually for the fluctuation process, now we want to prove that again it converges in distribution to random process. Okay, so this fluctuation process, okay, which is just written here, and it is the limit of the fluctuation process is the unique solution of this linear stochastic equation. Okay, so this is what we want to prove. Okay, and I'm not going to do again the proof. Okay, it's enough. It's enough. I completely understand it's enough for you and for me also. I would say the proof is more involved, but there is the same, it has the same scheme proof. Okay, so I'm not going to detail it. There is just that you have to, this is more involved because step 3, when you have to prove that the martingale times the square root of n converges to a G process, is you have to work a bit more. So this is the point. Okay. Just one slide and I'm done. We have extended all these techniques to the study of Bayesian neural networks trained with variational inference. Okay, so this is a joint work with Tom Hicks and Eric Moulin. So the framework is the following. So you are given a family of distribution Q, indexed by theta. Okay, and you want to find the arc maximum of the evidence lower bound function, which is just written here. Okay, this is the evidence lower bound function. It's an integral of here the loss function between y and your Bayesian two neural networks, okay, integrated over q theta, minus the Kullback-Leibler functional with respect to trial distribution. Okay, and you do actually what you do is you want to maximize, so you want to minimize minus the elbow, you use a stochastic gradient descent, okay, and you want to study, as we did before, the asymptotic behavior of the trajectory of the scale empirical distribution of, now not the weight, or if you can call it the weight, but of the theta k arising from the stochastic gradient descent. Okay, so you have a low large number. Okay, so this has been accepted very recently. We are working on the sample limit term, so it's everything is done, but you have to write it, and it's in preparation. Okay, so thank you for your attention.
Any questions? Yeah.
So you add this noise in epsilon. So if you don't have it, everything breaks down.
No, if you don't have it, it works. It works. You have the same result, except you don't, because you don't see the noise actually in the limit equation. Okay, the noise, except if beta is equal to 1/1/2. Okay, you don't see it. But if you don't have noise, it works exactly the same.
So the motivation for adding this noise was what? To have something which is more
To help exploring the yeah. And I would also add that when the beta is equal to 1/2, so when you have this Laplacian term, you have a diffusive term. So mathematically, the proofs are easier. Okay, because you have something which regularizes your equation. So it's more complicated when you don't have a Laplacian term. Okay.
Other question? I want to thank the speaker again, and for both last speakers, amazing time, considering perfect on time. Thanks.
Cool. Yeah. Thanks for the points. Now this kind of social part of the day starts. So we're going to take a group picture, and then there's the hike where hopefully you were able to check the information. It's not super hard, just in case you have some injury or so. Maybe check the we have to climb up some stairs, and there's a picture of the hardest bit. So yeah, sneakers should be fine, I guess, and sandals too. So maybe take a sip of water before we leave, unless you have a bottle to carry with you. There's some water, and then we meet in. Yeah, we take a picture in front of the entrance gate of the castle. In what did we say? In 12 minutes, I think. And I think the weather, I cannot guarantee that it won't rain, but the weather says that it won't rain. So at your own risk that it might still rain, who knows? But Google shows less than 10% chance for rain. So let's hope that it doesn't rain. Oh, we take the group picture now, and then we start the hike from there. And then we start at we can say, yeah, we can leave that here, and we come it's around, so we come back. So in 2 hours, we'll be back. So I would propose we leave it up here. I lock the door, we go back, and we can pick up the stuff when we're back in 2 hours. And yeah, we could say we start the hike at 5:20 at the gate. Okay. All right. Then we have 50 minutes of the 5:20 we start at the gate. And yeah, maybe take a little water. Oh yeah, and then afterwards, for those who are not joining the hike, we'll everybody who wants will meet at this beer garden at after the hike at like 7:30 and have some dinner and drinks. And it's outside, so yeah. I don't think it will rain, but I don't know how cold it will get, so maybe we'll need a shirt or something. I don't know. Cool.